Hello, I am recording the second video of the final exam review, and I realized that PowerPoint is not not good. It took too much time to encode the recording into a video file, so I regret using this. Anyhow, let me finish the second video. We are going to review the key concepts of each chapter. This review is it's not to replace the lecture. You need to uh, watch the lecture videos, and you need to read the textbooks. And what I would just want to do here is I just want to remind you of what we learned and what are the important concepts. This is for your learning, not only for the exam. So by just going through the major concepts, now maybe you can realize the big picture of what we have done and the outline and the main theme going through the different chapters. Okay, so let's think about chapter 4 and chapter 6. Chapter 4 and 6, chapter 4 is about single regressor, and chapter 6 extends chapter 4 into multiple regressors. So in those chapters, they set up the linear regression models and make notation and explain the basic terms and how we estimate the model. The terms are intercept and slope, and to estimate the model, we usually use the ordinary least squares method. Ordinary least squares estimates. This is what you see in the stata results, stata tables. And then you just need to understand the idea of the OLS method, not the algebra. And then based on the results, you should be able to interpret the estimated intercept and the estimated slope. And so intercept is the predicted value of the outcome if all the regressor equal to 0. And slope is the effect of a regressor on the outcome with all the other regressors held fixed. So that is the interpretation attached to the linear regression model parameters. And then also you should be able to predict the outcome, y. So it's easy, it's relatively easy given the estimates. And then in the results, you will see the R squared and adjusted R squared. R squared captures how much the model explains, how much variation in the outcome can be explained by the regression model. So if R squared is 1, then you explain 100%. If R squared is 0, then you are explaining nothing, right? It can be interpreted as the percentage of explanation power, and adjusted R squared is for multiple regressors. When you have more than one regressors, having additional regressor always increases the explanation power, regardless of its actual explanation, regardless of the explanation power of the additional variable. So adjusted R squared adjusts for the number of regressors. The more than so it's not only adding like the adjusted R squared does not increase if the additional regressor is not explaining anything, right? That's more natural. So we consider adjusted R squared for multiple regressor. When you compare two regression models with different numbers of regressors. And then, and when you think about multiple regressors, also you have to think about other regressors that are not included in the regression model. That is called omitted variables, and the omitted variables cause a bias. That is the omitted variable bias. And it's very important. Many problems, many problems in the regression models are associated with the omitted variable bias, some kind of omitted variable bias. And you can interpret the problem as a result of the omitted variables. And so it's important to understand how omitted variables cause the bias, the underlying mechanism. And then also it is important to guess the direction of the bias. So even if sometimes omitted variables cannot be observed, so you have to admit that there is an omitted variable bias. Still, it is important to guess which direction it is biased. The estimator is biased. And then how to remove the bias. It's simple. You need to include the variables or the related variables. And finally, multicollinearity is a problem. Multicollinearity, if there is a multicollinearity, then you cannot estimate the coefficients. And multicollinearity happens. The most common example of the multicollinearity problem is when you use dummy variables for multiple groups. When you use dummy variables, you need to drop at least one of the groups because one group must give the reference line, reference level, and the other groups are estimated as the difference from the reference group. So as I said, this is not about the full explanation of these concepts, but I'm just trying to remind you of what I did in the class. And I'm just explaining the key idea. So if you have no idea what I'm talking about, then you have to watch the video again. Okay. And chapter 5 and chapter 6 are also based on single regressor and multiple regressors. And these are the chapter 5 and 7 are more technical, more statistical. And the most important object in these chapters is the standard error. So of course you have an estimate, and then the second thing you need to get is the standard error, which measures the precision or the accuracy of your estimate. So the smaller the standard error is, the more precise your estimators are. And also standard error, there are formulas for standard errors, but it's calculated by Stata. So you do not need to know the formula, and I'm not going to ask you to calculate the standard error, but you should be able to calculate t statistic and p-value based on the standard errors, and also confidence interval, and also you must be able to tell if coefficient is statistically significant or not. So there are some technicalities in handling these things, and the formulas are pretty simple. So like and multiplying, dividing, or subtracting, adding. So these four operations are all, and p-value is slightly more complicated, but still it's doable. And you may use Excel or any calculator. So remember how to calculate those guys and what they mean. And in chapter 5, there is a case when X is binary. If a regressor is binary, the interpretation is slightly different, but nothing special. It's straightforward, but it's a special case. And also in chapter 5, another important topic is heteroskedasticity. So the idea is simple. Heteroskedasticity is not an assumption. It means it's a so this name is just the opposite of homoskedasticity assumption. When I was a student, in my textbook, there, like everything was assumed uh, based on the homoskedasticity assumption. But these days, no one believes in the homoskedasticity assumption. So people think everything is heteroskedastic. So uh, it is strongly recommended to use the robust standard error. Again, you don't need to know the formula for the standard error, but I want you to understand in what case homoskedasticity holds and in what case it's not. What is the intuition behind them? Okay, so those first four chapters are the same as the midterm exam. And now chapter 8 is about nonlinear models. Nonlinear models, the key idea here is that we benefit a lot by assuming a linear model. So typically in nonlinear models, the slope, the, the effect of a regressor on the outcome can be different at different points for different uh, people. So if everything is linear, beta, the coefficient beta describes everything. That's it. One number does all. But if the model becomes nonlinear, it's not true anymore. So if x changes, then the marginal effect of x also changes. So the examples of nonlinear models are quadratic term, so including the quadratic term x squared into the regression. Then calculating the slope requires a specific point of x. And also this is maybe more important, log variables, logarithm. If you take logarithm on variables, then interpretation changes a lot. Simply speaking, logarithm can be understood as a kind of percentage. Kind of percentage. Always log comes with percentage interpretation. So study how you can interpret the results. And the third example is on interaction terms. Interaction term is an additional term that multiplies two regressors. So this captures the change of slope. The slope may change. Slope may depend on another variable. So interpretation should be adjusted from the standard linear model. So these cases, there are a lot of different ways, different new aspects of the model that you have to think of. But the basic idea, basic principle is the same as the linear model. Like everything will be estimated by theta. You just need to change your interpretation. So practice how you interpret the results in these models. And chapter 10. Chapter 9 was skipped, so we go to chapter 10. Chapter 10 is about panel data. Panel data has entity dimension and time dimension. So you observe many countries over time. So you observe GDP of 200 countries over like the past 50 years, for example, or you observe the COVID confirmation cases every day in like say 50 states in and like in the past year. So then it becomes two-dimensional, like states and time, or countries or time. So panel data provide a more rich structure, more rich information, and that means we can control for the omitted variable bias in this form. So you can think about entity-specific time constant unobserved characteristics. So a certain state may have higher COVID cases than another state, maybe because a state is larger, has more population. Then it is natural to have higher number of COVID cases. And also there are some time-specific entity constant, time-specific but entity constant unobserved characteristics. For example, there is a big increase right after the Thanksgiving, for example. And Thanksgiving, the effect of Thanksgiving exists in all states, all 50 states. Then it is specific to the time, but every state has the same effect. So that is time-specific entity constant unobserved characteristics, like the fixed effect. To fix those model omitted variable problems, you may consider the fixed effects model. Idea is simple. You assign dummy variables for each entity or for each time and both in the model. So then it's like having different intercepts for different entities or for different years. Uh, Interpretation is also pretty simple. Like because everything is linear, interpretation is not much difficult. But what's interesting here is including the fixed effects may totally change the result. Like without fixed effects, the coefficient may be positive, but after adjusting for the fixed effects, the coefficient sign, the sign could be different. That's the example we considered in the textbook. So it's a very important model, and in the panel data, because we have 2 dimensions, you need to consider more complicated dependence structure. So the variables are correlated with each other, but on the 2-dimensional space, the relationship is more complicated. So I recommend to use clustered standard error. So implementation of fixed effects and cluster standard error in data are simple. And also interpretation is also very simple. So I think there is nothing much to talk about in panel data. So there is nothing special to say in to make a question out of this chapter. But I will try to make at least one question from this chapter. So make sure you study this. Oh, I think I spent like 10 minutes on explaining this, but by clicking on wrong menu, I lost it. So let me explain it again. I just did it. I don't like PowerPoint. So chapter 11 is about binary dependent variable. And the most important fundamental idea of a binary, when you handle a binary variable, is that its mean should be interpreted as a probability. So a binary variable takes 0 and 1 only. Yes or no, male or female, employed or not. So a lot of variables have this format, this form, 0 and 1. And when you predict the outcome, of course, the predicted outcome must be 0 or 1. If you predict the outcome to be 0.6, it means nothing. There is no outcome such as 0.6. Either you have to say yes or no, not 0.6. So 0.6, if your model predicts the mean is 0.6, then you have to interpret that the outcome is predicted to be yes, 1 with probability 60%. That is the correct interpretation. And then, if you understand this idea, the linear probability model is the easiest model to estimate a binary dependent variable. Linear probability model is no different from the linear regression model. Everything is the same. Like OL estimated by the OLS, standard error is calculated in the same way, like t-statistic p-value, confidence level, everything the same, R-squared, everything the same, but the interpretation should be different. You have to interpret the mean as a probability. And a linear model was very convenient in the earlier chapters because beta coefficient captures everything. However, now it is not ideal because we are handling probabilities. So by nature, of course, by definition, a probability must be greater than 0 and smaller than 1. But a linear model, a linear regression model, is a straight line. It goes straight forever. So at some point it goes greater than 1, and on the other direction, it goes negative at some point. Therefore, it's not appropriate for a probability prediction in some extreme cases. Therefore, the idea is, so if linear model goes like this, it will break 1 at some point. So the idea is let's make it curved. So goes, increases, but as it approaches to 1, it starts to curve and goes flat. And in the other direction, same. So it does not go down as straight as before, but now it's curved like this. So in the end, it looks like a S-shaped, or strange-shaped nonlinear function, smooth curve. And two most important nonlinear models for binary dependent variable are probit and logit models. Their mechanism is that if the regressor first determines, in the first step, determines the z index, which is a linear function of the regressor. So there is a linear index inside the nonlinear function. That is the first step. The linear index has no practical meaning. It's just purely, say, mathematical object. But it is easy to understand what's going on. So say there is a linear index, and in the second step, given the linear index, the outcome's probability is determined. If linear index is large, then you get higher probability, and if the linear index is low, you get lower probability. So the probability has direct meaning, like that's what we are interested in. So then, in this process, in this two-step mechanism, it's clear that the second step is nonlinear. So nonlinearity causes some complications, like because it's nonlinear, when you calculate the derivative, the slope is different at different points. As you see, the curve look like this. So flat, steep, flat. So slope can be different at different points. And also the second thing you need to be careful about in interpreting the results is that the coefficients have no meaning. The coefficients are the effect of regressors on the linear index. But linear index has no substance. It does not exist. So you cannot compare the coefficients across models. Like the probit coefficients and logit coefficients could be very different. And also they are different from linear probability model coefficients. So coefficients cannot be directly compared. Instead, you may compare marginal effects. Marginal effects calculate the effect of the regressor on the probability, not on the linear index. So marginal effect has the true practical interpretation, and this is what you can compare with the coefficients from linear probability model, right? And by the way, the textbook does not explain marginal effects a lot, but it's not that difficult. The idea is not that difficult. Mathematics may be a little bit more complicated, but I'm not asking you to understand the math, but the idea, what's the difference between marginal effect and coefficients, and why the marginal effects is complicated, and how you interpret that, and how the nonlinearity causes the difference. So it's pretty simple to understand the idea. And finally, the estimation principle is different from the linear regression model. The estimation of probit and logit models are not by the OLS method, but by maximum likelihood estimation. Maximum likelihood estimation is maybe the most important and method in statistics, or the most optimal, the desirable estimator in statistics. So that's why I'm explaining this. Its mathematical derivation is more complicated, but I skipped a lot. You just need to understand the idea of likelihood. We are multiplying the probabilities. So we would like to maximize the probability of what we actually get. Okay, this is it. And in the last, before recording this, I turned to the next page, but this is the last page. But if I turn the page, the recording stops. So I said a lot, but it was not recorded. So this is why I'm doing this second time. Okay, thank you for your work for the semester. It was nice to it was nice to uh, talk with you, some of you, and I don't know still most of you I've never talked with, but you know, good luck with your final exam, and feel free to email me if you have any questions, if you need any help. I'll be very happy to help you. Okay, see you later. Bye bye.